This is one of, if not the subject, most hated by students. But it's by far one of my favorites, both when I was studying and still now more than 20 years later. If you're wondering why, stay tuned and I'll show you. Here she is, my undergraduate thermo textbook. A bit worse for wear, but still has the same valuable ideas inside. Paging through it, I remember the first time I opened this book. It was completely overwhelming. In here are some of the most complex equations I had ever come across. Some concepts, like statistical thermodynamics, were very difficult to wrap my head around. But once I had made it through the whole thing, a light bulb went on. Once I saw the whole picture, I understood how powerful this is. As part of this series on what it's like to study engineering, I hope I can give you a broad overview, so if you ever start a course in this subject, you can feel confident about the destination and focus on enjoying the journey. Thermodynamics can be broadly classified into two pieces: mechanical and chemical. Apologies to the mechanical guys, but the mechanical bit is boring. Still, very useful and valuable, but it never appealed to me. Sadly, this is also the first part taught in courses, and so many students get stuck there and never get to the awesome bit. But more on that later. All of thermodynamics starts with 3 laws. If you've watched the first episode in this series, you already know the first. It is basically the rule of conservation of energy. In the thermo textbook, it is stated a bit differently. Although energy assumes many forms, the total quantity of energy is constant. When it disappears in one form, it appears simultaneously in other forms. We won't go into detail, but this is used as the basis for defining different types of energy. By doing so, we can apply the law and make sure they all add up. The second law is a bit more complicated and says no apparatus or machine can work in such a way that its only effect is to convert heat absorbed by a system completely into work done by that system. And also, no process is possible which consists only of the transfer of heat from one temperature to another. I know, this sounds a bit random, but those simple statements result in this. Yes, all power stations on Earth, which deliver the vast majority of our electricity, have been designed based on these simple rules. In fact, it was the creation of the very first machines that converted heat into work that led to the definition of these laws. One of the very interesting things that results from this law is the limitation on power generation efficiency. Every power station in the world does not deliver the same amount of electrical energy as the amount of fuel energy we put in. This is called the efficiency, meaning we always get less out than we put in. So, get this. For most power plants, the maximum efficiency is actually around 40%. That means more than half of the energy we put in is lost, and less than half actually gets converted into electricity. Very sad, but unavoidable. The laws must be obeyed. If you're thinking, but solar energy from those panels on people's roofs are different. Yep, they are. But their efficiency is even worse. Only around 20% of the sun's energy hitting the panel gets converted into electricity. On to the last law, which I'll only mention briefly. Explaining it would require a whole video. So let me know if you'd like me to make one. It says, as a system's temperature approaches 0 Kelvin, or minus 273 degrees centigrade, its entropy is at its lowest state. Sounds simple, but entropy is quite a beast. So these laws give us the ability to design anything from power stations to fridges, as well as cars and rocket engines. Well, that's great and all, but what about chemical thermodynamics? I'm glad you asked. So, imagine you're designing any chemical process. What's in it? Well, chemicals, of course. What does a chemical process do? It takes one set of chemicals or components, like ores or natural gas or oil, and transforms them into different, more useful ones, like steel or methanol or plastics. How? Well, by heating them and cooling them and reacting them. So how do we know how much heat is needed? Or how much pressure is created? Or what components do the reactions make? Easy. We just need their properties. Great. Where's the book or the computer that has them? Well, for some, the properties have been measured and you can look them up, but there are literally an infinite number. How could we possibly measure them all? And if you're doing something really interesting, like inventing new ones, they definitely haven't been measured yet. Let's consider some examples. When you boil water, at what temperature does it boil? 100 degrees, of course. Well, yes, but only at sea level. If you climbed the highest mountain in the world, it would boil way below 100. If you boil water, the gas you create is obviously water. Now, what if you boil a mixture of, say, water and methanol? Well, as it turns out, if you boil a 50-50 mix of water and methanol, the gas that is released is not a 50-50 mix. Instead, it will have more methanol than water. How could we have predicted these effects? Most chemical plants have hundreds or even thousands of components. How can we possibly get all the properties we need to design the process we want? Well, this is where the magic of chemical thermodynamics comes in. Using those same three laws, we can create mathematical equations which will predict the properties. Let's look at a simple example. You may have already heard of this one. It's called the ideal gas law. In essence, it says if we heat a fixed amount of gas, either the volume increases by a known amount, or if it's inside a container with rigid walls, the pressure increases by a certain amount. Now, if we heat up a gas inside a reactor, which is basically a tank with fixed walls made of steel, we can predict the pressure. From here, it can get a lot more complicated, but the principle is the same. If we want to predict the amount of a component in the gas when you boil a mixture, or we want to know how much of one solid dissolves in a liquid, we can use thermodynamics to derive the right equations to predict these properties. This is the basis of chemical thermodynamics. We start with the three laws, and then using them we can create equations that predict the properties of components as we heat or cool or transform them. Then we can predict how much electricity a power station produces or how much fuel a rocket needs to go to space, or how hot it gets when we react two compounds together. I hope you've enjoyed this quick look at the engineering subject of thermodynamics. Check out the other videos in this series and don't forget to leave a like. Cheers!